Okay, hello. I promised a video about the reduction of order technique we did in class and a derivation of the formula that appears in your web assign. And so here that video is, and let's get started. And let's get rid of this. Okay, so this is what the goal is. The goal is if you have a differential equation of this form, we're going to use second order, where P and Q are continuous functions, and it's homogeneous linear differential equation. And suppose we're given that y1 is a known solution. We wish to recover a second solution. Y, which is linearly independent from y1. And this is a form of the differential equation we're gonna take. And this is a formula which appears in your WebAssign homework things, and this is what we wish to derive. So let's just go ahead and start with the differential equation as so. And notice this Q never really appears. That's kind of interesting. And again, y1 is a known solution. So how do we get this new solution? Well, what we do, and this is a common technique here, is what we do is we attempt a solution of the form y equals some function u, and I'll write the u of x here. And I'll write the function u of x times is the known solution y. Oh, that's bad. Let's time y sub 1, the known solution, and see what happens. Well, since what we're going to do is we're going to take this and plug it into this differential equation here, we have to first calculate the derivative, and that's going to be u prime y1 plus u y1 prime. That's just a standard product rule from calculus. Now y double prime, because we have to plug in here, we have u double prime y1. We got to use the product rule here. U prime y1 prime. Then we use the product rule here very conveniently. And then we have u y1 double prime. Now, what we're going to do is we're going to simplify this a little bit. And we're going to write this in this order here. And then we're going to consolidate these two. And then we're going to have this one left over. Now, for this, I'm going to take P and multiply it by y prime. And that's going to give me P u prime y1, okay, plus P times u times y1 prime. And then finally, we're going to take q times our y. And I'm going to write that down here, q times u y1. Now, let's add these together. So I'm going to take this, plus this, plus this. So I'm going to add straight up and down. Now look at what gets added here. We can factor out a u, and we're going to get y1 double prime plus p y1 prime plus q y1. But remember, this is a solution to the differential equation, the homogeneous differential equation. So that's a big fat zero. So now what we get is we now get a u double prime y1 plus, now we got this here, 2 y1 prime plus p y1, okay, all times u prime, and that has to be 0, all right? So let's stop and think for a minute. Notice this differential equation has the second derivative of u and the first derivative of u. So morally, you can view this as a first order differential equation. That's why it's called a reduction of order. And what we do now is we let u prime equal this function v, and then u double prime is v prime. So we now get v prime y1 plus 2y1 prime plus py1. V is 0. Now, we could now divide through by y1, and let's do that. Well, yeah, let's do that. Let's not do that one. Let's not, so let's divide through by y1, assuming, well, y1's not 0, identically 0. So we have a 2y1 prime over y1 plus p y1 divided by y1 is 1. And now what we do is we move this to the other side. But now remember, v prime is really dv dx. So what we can do, we do the old separation of variables, although you could use linear first order here and get an integrating factor if you really wanted to, and that would work. So we could do this with the integrating factor, where it'd be e to this integral here, or what we could do is we can separate the variables, because we can write it like this. dv over v, dividing by that, is minus 2y1 prime over y1 minus p, all times dx. Nice separable differential equation. So now we do the good old, let's integrate both sides with respect to x. Like that. So now we slap on integral signs and do the integral. And everybody here knows what this integral is going to be. It's going to be log of absolute v. This here, now you got this 2 here. So you have a minus 2 log of y1. That's a substitution rule problem. I'll put absolute values here. Then this integral here, minus the integral of p dx. And we don't really know what this is because p is a given function that's going to vary from problem to problem. Okay. Now, let's go ahead and do some algebra. Let's move this over to this side. And now this part here, remember that log of a plus log of b is log of, let's just go ahead and do one more step in case that's saying, but this is log of v plus 2 log of y1 squared. Let's get rid of that too. That's what I did is I brought this in. Yeah. Then we can use the log addition formula. Now the log of a plus b is the log of a times the log of b. We've provided everything in sight is positive, and here this is the case. So we get now this. So now, So yeah, actually, when we did this integral here, implicit in this, there was a plus c. So I'll just go ahead and, yeah, when you did this integral, there was implicitly a plus c here. So I should have tacked that on here. And let's call that C1 just for grins. Now, if you take e of both sides, we have v y1 squared is equal to, now e to the c1, that say becomes k. This looks like an integrating factor kind of thing. And then division by y1 squared, we get v is equal to k e to the minus integral p dx divided by y1 squared. But remember v was u prime. So there's a more integrating to do. So we now want to solve for u. So to solve for u is going to be this integral here, and I'm not going to worry too much about this k. And then there's going to be, let's say, a C2. Now notice this C2 is, first of all, this k, it's not going to really matter because we just needed a u that has the right derivative properties. And second of all, this C2 here, if we really use that for our u way up here, well, we would be getting an extra constant multiple of y1, which doesn't really add to our solution. So it's actually safe to set your k equal to 1 and C2 is 0. You don't have to, but we can. That's the point. So now your u is what we said it was. So your new solution is going to be y is equal to y1 times this integral here. And that's with respect to x, which is what we set out to do. Now, we promised linear independence. So let's check linear independence. And let's go back to calling this thing u. So we had the first solution, y1. The second solution is this function u, y1. Now let's calculate the Wronskian because these are solutions to the same differential equation. That's going to be the determinant of y1, uy1, then y1 prime. And this part here is going to be u prime y1 plus u y1 prime. You take the determinant, we get u prime y1 squared plus u y1 prime y1 minus u y1 prime. Now, needless to say, these cancel out, so the Wronskian is actually equal to u prime y1 squared, and this is not 0 if both, here's the thing, y1 is not 0. So if y1's not 0, and let's see how to phrase this here. So if y1 is 0, this would be 0. So if it's not y1 0, and then u prime not 0, which means u is not a constant. But if u were a constant, then this would just be a constant multiple, and these would be linearly dependent. So assuming u is not a constant, then, and y1's not 0 to begin with, then these are linearly independent. Now, the next question is, so let's go ahead and use this formula here. And I botched this in my 9 o'clock class when I went to do this. So suppose we had the following differential equation, y double prime plus 2b y prime plus b squared y is 0. And we know that y1 equals e to the minus bx is a solution. And you can tell by the auxiliary equation, this is r squared minus 2br plus b squared is 0. This is, of course, plus. So this is really r plus b squared is 0. So this is our first solution. Let's find our second solution. Or our second solution, by what we have, your y is going to be this integral. It's going to be e to the, right here, e to the minus bx. We're going to have the integral here. And the minus p, that's minus 2b. Divided by y1 squared. Well, this is squared. This is going to be e to the minus 2bx. Now, this is going to be e to the minus 2bx divided by e to the minus 2bx dx. And this is going to be the integral of dx, which is going to be x e to the minus bx. And I know there's a plus c, but we don't really care about the plus c here. So this is your second solution. So what we know is that two linearly independent solutions to this thing. So the upshot is that all general solutions, all solutions are of the form a e to the minus bx plus b x e to the minus bx. Which is what I set out to do, solve in class, and you can see with this formula, it's quite easy. So thanks for watching.